All right, so let's just review a couple of the exponent basics before we get too far into this unit on exponents and the rules of exponents that we have to follow. So just some reminders about positive exponents we've worked a lot with before. So just remember that if you want to simplify something like this, 3 with a little 2 at the top, it's called 3 squared, or you can call it 3 to the second power. We use the number 3 as a factor 2 times, which means the base of 3 gets multiplied twice together. So 3 squared is 3 times 3, which can be simplified to be 9. So the number that you're multiplying repeatedly, we call the base. The little number that's raised after that is called the exponent. So in an example like this, we have 5 raised to the third power, which can also be called 5 cubed. So anytime something is raised to the third power, we can say cubed instead. And it just means that you're multiplying that base of 5 3 times. 5 times 5 times 5 is 125. Here's another example where we have 2 raised to the fourth power, which we don't really have like a special word like squared or cubed when something is raised to the fourth power. We can just say 2 to the fourth power, 2 to the power 4, or simply just 2 to the fourth, kind of as a little shortcut. You don't have to say the word power. And that just means you're multiplying the base of 2 together 4 times to get 16. Now, the reason why we use exponents is because it makes it a lot easier to write repeated multiplication. So rather than writing something like 9 times 9 times 9 times 9 times 9 times 9, we can count that there's 1, 2, 3, 4, 5, 6 9s being multiplied together. So 9 is the base, 6 is the exponent. So here's some examples just to show you, some of the things that we just reviewed or talked about. 3 to the sixth power is when you multiply a 3 times itself 6 times, you'd get 729. Another example, when you multiply the number 0 or a base of 0 raised to the third power, it's like multiplying 0 times 0 times 0, which is just going to be 0. Now, when we multiply with the base of 1, we're just showing that we're multiplying 1 together 4 times, 1 times 1 times 1 times 1, which is still just 1. So those are a couple of unique situations where using a base of 0 and a base of 1 is a little special, I guess, for exponents. Now it gets interesting. If we have a negative base, negative 3 raised to the fourth power means that we're multiplying negative 3 times itself 4 times. And in the end, that ends up being a positive 81, because when you multiply 2 negatives together, you will get a positive. And when you multiply these other 2, you'll get a positive. And when you multiply a positive times a positive, you get a positive. In my last example here, I'll show how you can multiply with a negative base and still get a negative answer. And in this case, you're multiplying the base negative 4 3 times. Now, think about what happens when you multiply a negative times a negative. Well, you get a positive. But when you multiply by that third negative number, it's going to make the overall value negative. So negative 4 times negative 4 times negative 4 is negative 64. So watch out for negatives when you're evaluating exponents. Let's talk about negative exponents. Okay, what we just looked at before, that was a negative base. That just meant you're multiplying a negative number repeatedly. With negative exponents, we want to think of it as the opposite of multiplying. It's like dividing numbers. And as we've seen previously, if you want to divide a number, it's basically the same as multiplying by the reciprocal of that number. So instead of dividing by 3, you can think of it as multiplying by 1/3. So in this example, we have 8 raised to a negative exponent, negative 1. So that's going to be like basically dividing by 8 or multiplying by 1/8 instead. So we take that, the base, and it gets moved to the denominator, and we basically just use a positive exponent once we move that to the denominator. So 1/8. Let's look at some more, though, because that can be kind of tricky. If we have 5 to the negative third power, we can think of that as taking, like dividing by 5 or multiplying by the reciprocal, 1/5, 3 times, because my exponent has a 3 in it. It's like 1/5 times 1/5 times 1/5, which it says the decimal form. I prefer to write this as a fraction. If you do 5 times 5 times 5 in the denominator, that's 125. So 1 over 125 is another representation of 0.008. And this is really going to show you exactly what I went through. Just, it's easier to think of it as, well, I'm grouping together these 3 5s in the denominator, so I can write that as 5 cubed in the denominator, which is 125. I want you to look at the similarity between having 5 to the negative third power and then having a fraction 1 over 5 to the positive third power. So we're basically just taking whatever this was, the base and the exponent. We're going to move that to the denominator of a fraction, just put a 1 on the top, but make the exponent positive when you do that. That's kind of a little trick we can do. Anytime there's negative exponents, we take that power, that whole thing, move it to the denominator and change it to a positive exponent. So here's kind of that rule that shows that relationship. If you have something with a negative exponent, we move it to the denominator. It stays the same, except keep the exponent positive then. And we can calculate whatever that positive exponent is to find the value of that fraction, or the value of that power. So here's some more examples just in table form. If we have 4 to the negative second power, we can write that as like a fraction, 1 over 4 to the positive second power. Notice it's the exact same thing, except we took the negative out when we turned it into a fraction, because it was like repeatedly dividing by 4. So it's 1 over 4 squared, which is 1 over 16. If we have 10 to the negative third power, and we have a base of 10, so we want to think of this as dividing by 10 3 times. So 1 over, so that's going to give us our 10 to the third power in the denominator, because that's like dividing by 10 repeatedly. It goes in the denominator, is like 1 over 1,000. Now, negative 2 to the negative third power, be careful with this. Your base of negative 2 is going to stay negative. The exponent of negative 3 is what's going to change to a positive exponent when we move that power to the denominator. So it's like dividing by negative 2 3 times. So 1 over negative 2 times negative 2 times negative 2, all in the denominator, becomes 1 over negative 8. Now, we're going to take a look at this table to kind of understand, well, why is it okay to just think of it as division? How do we know that that we're going to get those fractions and not negative numbers? So here's just a little table that hopefully will help you understand that. 5 squared, we know that that's just a 5 multiplied by itself, right? The exponent's 2, so I should see 2 of those 5s being multiplied together, and we know its value is 25. 5 to the first power, the 1 indicates that we're just multiplying a 5 once. In other words, you just have 5. Now, 5 to the 0 power means we don't have any 5s in our multiplication. So think about, well, what number is still there? Just like up here, we had 5 times 5, but it was really like saying 1 times 5 times 5. Or 5 to the first power, yes, there's a 5 there, but there's that invisible 1 that's with it. So it's like, well, 1 times 5, yeah, that's just 5. So when we don't have any 5s, because our exponent's 0, we still have that invisible 1 that's still there, making anything to the power of 0 equal 1. When we continue down this list, notice my exponents are getting smaller by 1. So 2, 1, 0, negative 1, negative 2. And we basically have just been dividing by 5, or taking a factor of 5 out of the value. So if we take this value of 1 and take a 5 out of it, or divide a 5 out of it, we'd have to do 1 divided by 5, which is like 1/5, or 0.2 if you want the decimal equivalent. And now if we take this 1/5 and we divide it by 5 again, because we want to reduce the exponent one more time, well, 1/5 divided by 5 is really like taking 1/5 times 1/5 again, which is like 1 over 5 squared. And like we saw before, another way to write this power is to move it to the denominator and make the exponent positive. Well, 1 over 5 squared is really 1 over 25, which is 0.04. 1 divided by 25 is 0.04. So that's just another way of looking at positive exponents that we're used to, and then kind of breaking it down into negative exponents. It's really all the same. If you increase the exponent by 1, you're making it 5 times larger because the base was 5. If you're decreasing the exponent by 1, you're actually making it 5 times smaller. So you actually have to divide the 5. We also want to be careful about grouping anytime we're working with exponents. As we see in a few examples here, when we have -2 squared with the parentheses around the -2, that implies that -2 is actually the power, or excuse me, -2 is the base, 2 is the exponent. So I want to multiply -2 by itself twice. So we end up getting a positive 4. If we don't use parentheses around that -2, what it means is that we're taking the opposite of 2 squared. So we actually evaluate the 2 squared first, which is just 2 times 2, and we keep that negative sign in the front, making our answer -4. So -2 squared with parentheses equals positive 4, and -2 squared without parentheses equals -4. So something to watch out for. Another example, when we have with parentheses, this time with variables, if we are grouping together AB and squaring it, that means A times B multiplied by itself twice. So AB times AB. If we don't use parentheses, however, and it just says AB squared, the exponent is only applied to the B. It's just like saying A multiplied by B squared. In other words, A times B times B. So it kind of gives us a little different situation because I only have the A once in that second example where I had the A show up twice when it was grouped with parentheses. All right, now let's talk about negative exponents when there's variables involved. It's just a little bit different because we can't just think of it as dividing by that number because they're variables. So if you have a negative exponent in the numerator, the top of a fraction, or if it isn't even a fraction, think of it as being in the numerator. All we have to do is move that power, move whatever that thing is, to the denominator and make the exponent positive. In this example here, what we would do is we would think about it as keep everything as a positive exponent the same, and we move just the k to the negative first power down to the bottom and make it positive. So I'm going to leave my h to the third power on the top because it was already in the numerator. On the bottom, my 6 is still there. My m squared is still there. But now I also have this k raised to the first power in the denominator. Now, a couple things. I change my exponent to a positive 1, but I do not need to write the positive 1 as an exponent because anything without a visible exponent is raised to the first power. Like x is the same thing as x to the first power. So I don't really want to put that 1 there because that wouldn't be proper. In our other example, it says for a negative exponent in the denominator, so on the bottom, what we do is kind of the opposite. We take that whole power and we're going to move it up to the numerator and we're going to make it positive instead. So keeping everything else the same, I have s to the 5th power in my numerator, and I'm going to move the entire power to the numerator. T to the negative 12th power becomes t to the positive 12th power when I move it up. So that fraction bar is kind of like if you move something up or down across that fraction bar, you have to flip the sign. Positives become negatives, negatives become positives. Then the other thing is, now that we have really nothing left over in the denominator, it's that invisible 1 left over. And to simplify this, anything divided by 1 is itself. So we really don't need the denominator at all. We don't even need the fraction bar because the s to the 5th power times t to the 12th power divided by 1 is just s to the 5th power times t to the 12th power. So let's look at just a few more examples and then we'll wrap things up today with our video. So here we have 3 times y to the negative 2nd power. First thing to remember is that those are 2 separate things. It's like 3 to the 1st power and y to the negative 2nd power. So if we want to simplify this expression, that means we can't have any negative exponents remaining. So I am going to need to move that power, I guess it's, well, right now it's in the numerator, so we'd have to move it down to the denominator. My 3 is going to stay in the numerator because that had a positive exponent. And we move the y to the bottom and change the exponent to a positive 2 instead. I don't even need that invisible 1 there anymore because anything times 1 is itself. So it's not necessary to write that in there. So it's just 3 over y squared. All right, with this one, we do have a negative power in the denominator. Notice in the numerator there's a negative number, but that's not an exponent. That's like negative 4 to the first power. That's a positive 1 for an exponent. So we're going to leave the negative 4 where it's at. Negative 4 stays in the numerator. And we need to move then, because our negative exponent is in the denominator, we want to move it up to the numerator. I guess I need to make this a little bit bigger. I'm going to move the k to the top and change my exponent to positive. And then what's left over in the denominator is just, well, there was nothing there, so it counts as 1 because it was like that invisible 1 being multiplied by k to the negative 4th power. And anything divided by 1 is itself, like we saw earlier. So I guess I don't even need this. Let's get rid of that. Negative 4 times k to the 4th power would be the simplified form. All right, number 3. This time we have 2 terms, 2 different powers with negative exponents. So we're going to need to take the g and move it down when we make our exponent positive. But we also need to take the h and move it up. Because it was in the denominator, we're going to need to flip it to the top to turn the exponent into a positive. So when we do some flipping around, remember to change the exponents to positive anytime you move things around like this. So g to the negative 3rd power in the numerator is going to become g to the positive 3rd power in the denominator. Then the h to the negative 6th power in the denominator, when we move it up, is going to become h to the positive 6th power. Now I have everything with a positive exponent, so it's simplified. One last problem. Number 4. All right, this time we have, it looks like the x to the negative 3rd power has a negative exponent. We've got b to the negative 2nd power has a negative exponent, so we need to move that. So the x's we're going to move down, the b's we're going to move up. And then there's actually one more thing we can do here with this a to the 0 power. Now that's not a negative exponent, but we did talk about anything to the 0 power is equal to 1. So we can actually simplify that also. So let's do some moving around. The x's are going to go on the bottom, change it to a positive exponent. The b's are going to go up to the top, change it to a positive exponent. And for that a to the 0 power, that counts as just a 1. Anything to the power of 0 equals 1. This can be simplified just a little bit further because 1 times anything is just itself. So let's rewrite this as b squared over x cubed. Let's kind of make that 1 invisible. All right, that's it for today. Thanks for sticking with it, and good luck with your homework.